Hello and welcome to WCT's video tutorial series. In this tutorial, we're going to talk about how to use software Wavenology to study the EMC/EMI issues of a PC box. The outline of this presentation is listed as the following. First, we're going to talk about the EMC issue of a PC box. We're going to study the cavity resonant frequency with various internal structures, and also the EM leakage from the FEM window and open slot, some very typical structures on the PC box. Next, we're going to study the EMI issues of a PC box. Typically, it's an ESD on a closed PC box, ESD on an open PC box, and the resonances with sharp and wide pulses. So to begin with, let's start with the first section. EMC issue of a PC box. Like this simple model, the PC box may contain internal supporting frames and for separation and mechanical purposes. It might also have the fan window for the thermal and cooling system purposes. Also, like an open slot here is very typical for CD drives. So we're going to start to build this model and study its resonances and EMC issues step by step. So now here is the empty project in the software Wavenology. We're going to start with the design tab, as always. So first we check the unit. As for PC box, we want to use centimeters here. And time, let's do nanoseconds, and frequency range is around, the unit is around gigahertz. So click apply. In the background, let's do air. The boundary condition, let's keep all of them open since this is a open bounded problem. So for the frequency, we leave it as the default since most of the EMC/EMI signals are within gigahertz. And the mesh, let's do 20 for points per wavelength. That's the sampling density. Time, let's do user defined with 120 nanoseconds. And we do want to see a very smooth animation, so that's why we increase this sampling density over here from 2 to 5. Okay, so that's pretty much the basic parameters for this project design. Next, we're going to draw this PC box. The feature I'm going to use for this PC box drawing is to use some variables. So if we click here, like variables here, we can define the variables in this dialog. So for example, I make the length with the value of 20 centimeters, and click add. And I made the thickness TH to be 0.30 centimeters, that is 3 millimeters, and click add. And for the other purpose, I will create an offset and put it as 3 centimeters. This is used for building geometries like the fan window of the PC box. So we define 3 variables, and when we build the geometry, we can use these variables to simplify some calculations. So for example, let's first build a PEC, perfect electric conductor box. Let's start with XYZ coordinate from 0, 0, 0 to length along X direction, and length times 2.5. This is a nice, beautiful part of using variable, because you don't have to really use numbers to do the calculation, just to make the ratio. Length times 2.2. So let's see how this box looks like if we build it this way. So as you can see, it's a brick filled with perfect electric conductor, which is metals. So next, let's it's empty box just with a metal cover. So we dig a air box inside this PC. So again, I use a material air, and then here I use the coordinate to be TH, 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 len minus TH, len times 2.5 minus TH, oops, and len times 2.2 minus TH. So TH is the thickness, so I create a smaller air box inside this PC box and dig it out. And that will tell me, this is dialog asking, okay, so which kind of material you want to use, since there's overlapping region. So I'm going to use the new solid. That means I'm using the air, and I create it. From here you won't see any change, but if you make the transparency a little larger, and you will see actually it's empty already. Okay. So again, if I since this internal air box is already there, I'll just go ahead and delete it. And now you will see actually there's a PC box now. Okay, with some thickness that we define in a variable. Alright, so that's as simple as building a PC box. Okay, so next let's see how to build a source into this cavity. So we want to use a dipole source, point dipole, inside this cavity and excite a pulse and see the survival frequency modes that this cavity will support. So first let's build this point dipole source. I want to use electric dipole. Its polarization, I want it to be arbitrary direction so that it can excite as many modes as it can. So I want to use 1, 1, 1 polarization. And the position I'll just use 10, 25, and 10. So let's see where it is. Alright, we have an indicator over here that is showing this point dipole source. Right, as you can see, it's within the cavity and it's pointing towards the 1, 1, 1 direction, the vector direction for this point dipole. Okay. So next, let's build the observers. We want to see the field probes in several places. The first probe we want to build is inside a cavity, like 10, 25, and 20. And we want to observe all the field components. So we create. So here we put in 3 field probes to observe the field. So let's see, if you click the first probe, it highlighted with a blue color right here, and you will see it's inside the cavity. Okay, to observe the field. And to check out if there's any field leakage, we can see the second observer I put right over here outside the PC box, and third one is close to this corner, but still outside the PC box. Okay, so now we have the 3 field probes, 1 inside, 2 to the outside. Next, we want to observe how the field is resonating inside the cavity. So we want to build a phase snapshot. And the way to build it is here, snapshots, right click, create phase snapshot. So within this dialog, we can build a phase cut through the entire computation domain. The position we can use is, for example, I put in 3, minus 10, minus 6. And again, because it's an X phase cut, so I'll put in the same coordinate, 3, 60, and 52. And click OK. So you can view where is this position is. Now I'm going to create another one, which is the Y phase. So X, I'm going to start from the lowest corner, which is minus 4, right over here. And the Y, I'm going to start with 6. Also Z, I'm using the same. This will be 24, 6, and 52. Okay. And you will see this is the Y phase cut. Okay. So now we have field probe, snapshot of the field propagation and resonances. And we also want to observe the far field. The far field can be defined over here. We want to do the wideband RCS monitor. And here the software is using the spherical coordinates, so you need to specify the angle and distance. So theta, if you put theta into 90 degrees and phi equals to 1, and the distance put in 30 meters away, we will have an indicator showing that you have a point outside this computation domain. Actually, it's 30 meters away, but you can really not draw the indicator 30 meters away. That's too large, too far away. So we just put in the position direction indicating this is observer point of the far field. Okay. So that's pretty much it. We can start a simulation and check out the results. If you click this button right here, it will start to simulate. Okay. If you want to, you can also check the mesh. As you can see, the detailed thickness can be captured with the FDTD mesh. Right. So this simulation is going to take a while. I've already pre-simulated everything, so we just directly load the result and check how this PC box is radiating without any features added. So after the simulation, you can see the results showing everything here: excitation pulses and also the transient results. So first, let's check the excitation pulses. This is the pulse we're using. It's a pretty sharp pulse. As you can see, it's a BHW function. The pulse width is from 0 to around 3 nanoseconds only. Okay, it's pretty sharp. And with this pulse, if you analyze its spectrum, actually it covers from right about 0 to 1 gigahertz. It has all the frequency components contained in this transient pulse. So after that, let's check out the transient behavior. So you give that shape like BHW shape, and now we want to observe the EX, EY, EZ. If we check all the results, you can see there's only one signal surviving. That is the first observer, which is inside this PC box. The other two are all 0. This makes sense because the metal shielded everything, and nothing comes out. Okay. So if you check out the other components, you can see it's about the same behavior. Now, what is interesting is we want to see the resonant frequencies survive in this cavity. So we have the spectrum frequency domain results. You will see this is actually the resonant frequency. We can observe the first resonant mode is around 0.46 gigahertz. Okay, that's the first resonant mode. Second mode is 0.75 gigahertz. Okay, and third higher mode. Okay, there is the analytical formula that you can calculate the cavity resonance frequency modes. But here we just assume that you already have some background about calculating the resonant frequencies for PEC boxes. Okay. So that is only the curve data. The powerful part of using the 3D simulation is to visualize the field everywhere, and that's the advantage of using the snapshot. Okay. So here is a transient snapshot. If we load in all the results here and use the log scale, I'll hide the field vector. As you can see, this is point dipole bringing in the field within the PC box. But when it's touching the PC box boundary, you can see the field cannot go out at all. It's all enclosured inside this PC box. So the pulse has already passed, but there does have some surviving modes that is keep oscillating back and forth within this PC structure. Okay, that's how you observe this resonances. All right, that's a transient display of the field propagating. Now, if you do want to observe the field distribution at a certain frequency, for example, we observe this mode. The first mode is, let's see, 0.46 gigahertz. You can easily do it here. 0.46 gigahertz. Click OK. It will take a second, only less than a second to calculate. And actually, this is how the field is distributed at that frequency, okay, within the box. So that's actually exactly the TE101 mode for this cavity. Now, if you want to check the higher mode, for example, let's see, the second mode is 0.75 gigahertz. Let's say about that. Then we add another frequency, 0.755. gigahertz. It's easily done. And you check out all of them. You can see this is the second resonance. You have two standing waves along this direction, and that's how the resonance is supported. Okay? So this is the second mode. Now, this cavity resonance is easily studied and displayed very straightforwardly. Now let's check out the far field. So we already have some assumption here, is because this dipole source is enclosed with the metal box, nothing comes out. So really, outside the box, you will see zero field everywhere. So the far, not only the near field as you observe in the observer, but also the far field as well. So this actually predicts the same thing, that nothing comes out from this fully enclosed PC box. Okay, so that's the first example. Now, before we check out the radiation and EMC issue, we want to study the second thing is, if we change the internal structure. This is very typical if you have a motherboard, graphic card, also some mechanical metal frames within this box. What is going to change the property of these resonances? Okay, so let's first build a metal board right around here, and see how to change things. So the position here we use is TH20, and here is 10, 20, and 20.5. Okay, now you see I built a board right over there, which is touching only part of the PC box. Okay, you see it's not fully separating the PC box, only part of it. Now let's see, keep everything else the same, and see how this board will introduce some new characteristics, new properties into this resonance. Again, I've pre-simulated everything. Now let's check out the result over here. This is identical to the model I've built. Now first, let's check the transient signals. Again, let's check out EX. Okay, doesn't seem quite different as compared with the first one. Again, the two field probe outside the PC box has nothing. The internal probe can detect all these oscillation signals in transient domain. But if you check the spectrum, now you will see, other than the first mode, here is still 0. Well, it's a bit low. It's a bit lower than the original one. Original one, remember, it's around 0.46. Now it's dropped down to 0.44 gigahertz. And there are some other modes coming out, like this one at 0.63 gigahertz. The second mode actually is 0.75. That remains around about the same. But you do see that there's extra modes coming out due to introducing this new board inside this PC box. So that indicates, if you have a complicated structure, internal structure of your PC box, you will have a lot of resonant modes that will be excited with some ESD signals or sparkling effects. Okay, so we got to be careful with that on the frequency changes. Again, let's see how this field is being resonated. So we visualize this snapshot again using log. I don't want to display any arrows here. Okay, so now you see it's obvious that this metal board is separating the field into two regions, and that's why it's bringing the new resonant mode. You will see the field has a more complicated pattern inside the structure, and it's oscillating at more frequencies. That's how we say it's more resonant mode is supported. Okay. So what is interesting is actually the right over here is the touching point of the board. If you go back to the 3D structure, that is actually right over here, this corner and this corner. So if we go back and pay attention to that, to the snapshot, you'll see after it's resonating for a while, you begin to see the strongest point is actually on the joint touching point. This is a singularity point in the geometry, and that is why it is accumulating a strong field over there. So anything that is trying to avoid the strong interference, I need to stay away from this corner, especially when it's touching the another board. Okay, so that's a useful hint we can get from this type of simulation. So if you want to see the field pattern, let's go back to the resonant modes here again. Let's see the first mode, how the field is going to distribute at that frequency. 0.43, I would say 7. 0.437. I add that frequency. 0.437 gigahertz. Now let's see how this pattern looks like. Alright, that's how this pattern looks like. As you can see, it's resonating like this. Just keep doing the things like this. Okay. So if you go with the higher mode, see the more complicated pattern. Let's see if it goes again 0.753 gigahertz at another frequency. 0.53 gigahertz. Now you see the pattern is a little bit changed, but it remains roughly the same as the previous one. That's why the frequency doesn't shift much. Okay, so this is how the adding one panel introduced a new modes here. Now if you want to observe, do observe the newly introduced one. Let's see this one. 0.635. And let's see how does this new introduced mode looks like. Alright. Okay, so it looks like that this new mode only occupies around half of the space within this cavity, and that mode is still supported. Okay, that's how the field pattern at this frequency can be visualized. Again, emphasize again, it's the singularity point really accumulates strong fields. Okay. So that's about adding one panel here. I changed a lot of things already. Now what if we make things more complicated by adding another supporting structure? For example, this one is mimicking a graphic card. Now I'm adding a huge panel here that is separating the entire PC box from the hard drive part or the mechanical supporting frames. So let's see how it will impact. Alright, so again, I've already pre-calculated the geometry parameters, so let's just add another pad. Material I use, again, steel metal. The position I would say is TH 36 centimeters and TH, the thickness, and 36.5 and 2.2 times length minus TH all the way go up. So now you will see it's a frame, very typical in the PC box. So again, I pre-simulated everything again here, identical to the previous one. I leave everything, the source, observer, everything the same before. So let's check the result. So if you check the spectrum here, the magnitude of EX, now you will see that the mode remains there. It's still 0.441 gigahertz. Second one is much stronger, 0.53 gigahertz, and this one 0.73. The 75 one is kind of lowered, and there are more modes coming in. Okay, so let's see how these things are. The pattern looks like inside the cavity. Again, this is transient data. It will show the field started from the dipole source, and now you will see that actually, although it's separated most by this by this board, but field will still coupling through the other side of the box. Okay, as you can see here. So you can see the field is keep oscillating, stronger in this side, weaker in that side. but it's everywhere inside this cavity. Okay, so if you check the pattern at a certain frequency, let's see we don't want to observe let's see the first mode, 0.416. The patterns here, so you can observe that it's pretty similar to the previous one. Yeah, that still survive this mode. Now let's see the higher one. Let's see 0.528. By 528. If I'll use linear scale. Okay, it's pretty much that's how the pattern looks like for that frequency. Okay, very strong in the singularity points. See if we have a higher mode over here. Let's check the most complicated one, the higher mode. 0.883, I would say, gigahertz. See how the pattern looks like. Alright. So now you see the pattern really at this frequency is resonating in this way, and the strongest point is located over here. So any structure added into this PC box will change the field pattern and also change the field resonant frequency. So that's how we finished the first topic right over here, the cavity resonant frequency with various internal structure. Next, let's check out how the EM leakage from the FEM window and open slot. So let's first draw a small window here using the air box. This is air, and we want to change the local coordinate system origin to be length minus th plus offset. So this is what be my 0, 0, 0 for the local coordinate system, and then we use 0, 0, 0, th, and 1 and 1. We want to use the new material. So as you can see, I dig a small hole over here. Okay. So after I have this single small window, I'm going to array copy. I select this small window, right click, and then the array copy here. It will be along the Y and Z direction. So this is a 2D copy. Along Y, I'm going to leave a displacement. And I need 10 of them. Along Z direction, I will need a same displacement. And I will need 5 of them. And I delete original. So whenever you have a new solid, it's asking the overlapping region which material you want to choose. So I'm going to use the new object for the following for all of them. Alright, as you can see, this array of the FEM window is being created. Okay. So now we're going to simulate how this thing will bring the difference. Is there any field that is going to coming out? The EM leakage is going to be okay, or still we need to have some concerns about it. Okay. Now you can see the field outside is no longer 0 anymore. Okay, it does have some values, right? So if you compare all of them together, you will see the strongest one is still the field inside. The field outside, although it detects non-zero values, but compared to the inside, it's not in the same level. It's almost 0 compared to the internal field. But if you zoom in, you do see that the field is non-zero anymore. Okay, and the position right near the FEM window has much stronger amplitude than the field probe, field level detected at the top corner right over here. That's how we see the transient signal being radiated. So let's see the snapshot over here and see how they change stuff. I'm going to use the log view. Yeah, again, I don't want to display the arrow. Okay, so you see most of the field is still constrained within the box, and this FEM window, let's check out. Does it really radiating a lot of stuff? You see something are coming out, but not much. Okay, now if you want to see it clearly, you only leave this one. Let's see if the field is really coming out. Okay. Alright, the field is already very strong inside, but actually if you see from through this FEM window, it does have something coming out, but it's not radiating. It decays very, very fast, almost to zero within few millimeters. Okay. And if you want to check the frequency at a resonant frequency, you will see that it's really coming out, but really decaying really fast and not radiating. Okay. So in conclusion, we can see that the FEM window is much smaller than the wavelength, because at 1 gigahertz the wavelength is around 30 centimeters, but this FEM window only has a few millimeters wide, so really the field is not going to coming out. So it's pretty safe and secure to add this FEM window when the hole is much smaller than the wavelength. And that's similar to the microwave oven. From the simulation, you can see that as long as those holes are really small, the EM field leakage is really weak. Okay, so it's pretty safe when you get close to the microwave oven looking through the window. Okay, so that's about this simulation. Next, based on the FEM window, we know FEM window is secure, but how about the CD drives? Okay, if you have a much larger open slot on the PC box, and what is the radiation looks like? All right, so you can see I dig a hole on this PC cover, metal cover again, and my third field probe is right over there, just outside this window. Okay, so we want to simulate everything again and see how it does impact the radiation. So as you can see now, the internal field is really still strongest among the three, compared to the field that is sitting outside. But if you display the second one and the third one, you keep notice that the second one is the one that is close to this window, and the third one is close to this FEM window. Okay, so we see stronger field at this position than on the close to the FEM window one. Okay, so we do have field that is coming out, although it's still weak. But does that going to radiate? Let's take a look. The first we do the transient result. You see the field is still coming. Compare everything. There's not much coming out compared to the internal field. Okay, so if you only observe this window, this field is coming, and you will see that there's little thing coming out, very little. Alright, keep oscillating, but this little thing might radiate if you change the frequency. Let's say the third resonant mode, and we check over here using the log algorithm. You will see the internal has the strongest field, but really the field outside the PC box is really everywhere. Okay, as you can see the radiation at this resonant mode. Okay, it's radiating from the hole, coming all the way surrounding this PC box, and it's radiating. Okay, that's the near field pattern looks like at the this frequency, the third resonant mode. Now if you check out the far field Let's go back here. Again, at this frequency, if you display that, you will notice that at far field, the strongest point is at right around this angle and around 45 degree down to the angle. So you know, if you observe the field really far away, like 30 meters away, you will see which one is the strongest point. Okay, so that's how the radiation pattern looks like when you do the EMC. Now, what need to be mentioned is not only the intensity of the radiated field, but also the polarization. If you show the polarization here, you will see most of the field is oscillating vertically. So if you have a field probe that is lining up horizontally, then you will not detect any field that is coming in, and you might pass the EMC test. But if you make it vertically, you might fail the EMC test. That explains why, because the field polarization is not lined up with your radiation patterns. Okay, so that's how we analyze by adding in the internal structures. How does it change the resonant frequency? By adding in the small window, it doesn't bring much about the radiation. It's pretty safe to add the small windows, but if you have big slots, especially when it's comparable to the wavelength of your excited pulse, then it's really need a concern when you're trying to make some EMC solutions. Okay, so that's how the software is really helpful to help you intuitively understand the structure change or bring the EM property change of your designed devices and systems. So that's all for using the software Wavenology to study the EMC effects from a designed geometry. And thank you for watching.